Okay, so we have Travis Mandel. He will talk about classification of Looijenga interiors in 2 lectures. This is the first part of the lecture.
Thank you. Thank you for putting together this conference and inviting me to speak, and scheduling my talk to work with my own schedule and with the time difference and everything. I appreciate that. So so today I want to tell you a bit about the classification of Looijenga interiors. Basically, just I'm going to give a bunch of different properties that you can use to describe Looijenga pairs, Looijenga interiors. And then have a whole bunch of statements of the form, the following are equivalent, and have a bunch of equivalent statements that, if your Looijenga interior satisfies one, satisfies all these others, and it helps you get some intuition for the properties satisfied by whatever Looijenga interior you're interested in, whatever you're working with. So start with some basic definitions. Apologize if I'm repeating stuff from other talks. But probably good to see the basics again. So a Looijenga, switch the highlighter. So a Looijenga pair is a pair y comma d, where y is the data of a smooth rational projective surface. We'll say over the complex numbers, or really over any characteristic 0 algebraically closed field. And then D is a choice of singular, nodal, anti-canonical divisor. Anti-canonical meaning that it is in the class of negative ky. Ky is the canonical class, so negative ky is the dual, and so it's in that linear system. Effective curve. So singular, so we actually require that it has a node, but it doesn't have any singularities besides nodes. So the most basic example is, some of the most basic examples are where y is equal to P2. And then D, some examples of D might have a nodal cubic. So maybe D is something like this, or D could be a conic in a line. So remember for P2, so negative k P2, so that's O of 3. So D should be a cubic. So we could have a nodal cubic, or we could have maybe a conic in a line. So just a degenerate version of the first one, or we could degenerate more and have D is 3 lines. So these would all be different choices of D, and these give very different Looijenga pairs. If you choose different nodal cubics, that will change the pair y comma D, but basically like the main properties of the geometry we won't care about, or they won't change too much. We will mainly be considering Looijenga pairs or Looijenga interiors up to deformation. So different nodal cubics, those deformations won't matter, but the difference between this or this or this, those will be significant differences that give you non-deformation equivalent things, very different pairs. Now a Looijenga interior is just the complement of D. So it's we'll denote it by U, and it's the set y minus D, where yd is a Looijenga pair. And then y comma D I might call a minimal model for you. So some examples you could consider, the most basic examples are where y is a non-singular complete toric surface. So you just take a fan that is complete, fills up the whole plane, and is non-singular. The corresponding toric surface is that toric variety together with its toric boundary is a Looijenga pair. And then no matter what fan you use, no matter what your toric surface is, the complement of the toric boundary, it's what we call U, that'll just be the algebraic torus, C star squared. And so notice if you change your fan, that doesn't change U at all. That only affects the boundary, not the complement of the boundary. So more generally, we can look at toric blowups. So toric blowups are basically changing your fan. without changing U. So we'll say a simple torque blow up of a Looijenga pair y comma d is, well, basically it's a blow up of y. So it'll be another Looijenga pair y tilde d tilde, where y tilde is, we have a birational morphism from y tilde to y, which is just blowing up one of the nodal points of d, and then d tilde will be the inverse image of d. So we have, here's our d, we choose a nodal point of d, and we blow that up. Something like that. So it's a generalization of refining your fan, adding new rays to the fan for a torque variety. So yeah, just blowing up nodal points of d. And then more generally, a torque blow up will be a sequence of non-torque blow ups. So you'll blow up a node, take the inverse image of d. Now you have some new nodes. You can blow up those, keep blowing up. And as I've mentioned, the key thing to notice is that torque blowups don't affect U. You're only adding new stuff to the boundary, but U is not changing. In contrast, we'll also consider non-torque blowups. So this will be how we actually get different Looijenga interiors, how we change U. So a non-torque blowup will be, again, a birational morphism from y tilde to y. So a blow up from y tilde, blow up y tilde to y. This time we'll blow up at a non-nodal point of the boundary d, and then d tilde will be the proper transform of d. So here we have our boundary d, and instead of blowing up nodal points, we're blowing up non-nodal points like this, getting some exceptional divisors. And these exceptional divisors will now actually live in U. Like other than the point where they hit D, the exceptional divisor will be added to U. So these actually change your Looijenga interior. So starting with just a torque variety, you can do different non-torque blowups to get a whole bunch of different new Looijenga interiors. In fact, as we'll see in the next couple slides, you can get all Looijenga interiors that way. So a torque model is a birational morphism from your Looijenga pair down to a toric Looijenga pair. So this phi bar d bar here is a toric pair. Y bar is a toric variety, d bar is the toric boundary. And then this birational morphism pi is going to be a sequence of non-toric blowups. And Groshacken and Kiel found that every Looijenga pair has a toric blowup which admits a toric model. So initially you might not be able to blow down to a toric variety. For example, if you have, like I mentioned, the case of where y is p2 and d is a nodal cubic, there's no way you can blow that down to a toric variety because your boundary is just one component and you can't have a complete toric surface with only one component. But you could blow this node up and then blow up another node. And after, let's see, 2 or 3 blowups, I think, then you can start blowing down. You can blow down various -1 curves that hit the boundary until you get down to a toric variety. And the fact that you have to take toric blowups first, that's not a big deal because for this talk, at least, we're mainly interested in the interior, the Looijenga interior, and these toric blowups don't affect the boundary. So the upshot then is that you can get every Looijenga interior by doing non-toric blowups of toric varieties. Non-toric blowups of toric. So this says, every Looijenga interior can be constructed, as I said, via non-toric blowups of toric varieties. So one example, consider where y is a cubic surface, d is a triangle of lines, and then u is the affine cubic surface. So a toric model for this is we can start with P2 and D is a triangle of lines. So here's our D. So we could say these are maybe the x-axis, y-axis, the axis at infinity, or z-axis.
So Travis, can you maybe say what a cubic surface is in case there are some people who doesn't?
Yeah, so a cubic surface, well, you could say it's a hypersurface in three-dimensional space, living in P3, defined by a three-dimensional or a degree 3 polynomial. But the useful characterization for us, and this is a an important fact, kind of a classical thing that's in Hartshorne, but it goes way back. You can always construct a cubic surface by blowing up 6 points in P2. So if you blow up 6 generic points in P2, you get a cubic surface. Meaning, a surface cut out by a degree 3 polynomial in, say, the homogeneous variables x, y, and z. Or sorry, in the homogeneous polynomial. But yeah, so we can construct this by blowing up 6 points in P2, and I'm going to choose those 6 points to live on the boundary divisors. And if I chose my 6 points somewhere else, whatever generic 6 points I choose, you can just take 2 of them, take a line through them, take another 2, take a line through them, take another 2, take a line, and say that those 3 lines are your boundary. You can kind of work backwards, choose your boundary to fit whatever your blowups are. And this way your cubic surface can be viewed as taking P2, taking 3 lines, blowing up 2 points on each line. So you blow up these 6 points, get 6 exceptional divisors. Now, let's see. Right, and so now this will give you a cubic surface now because we've blown up 6 points in P2. This classical fact is that can be realized as a cubic surface. If you see, and another standard fact about cubic surfaces is they always have 27 lines. 3 of those lines are the boundary. Another 6 of those lines will be these exceptional divisors. And then your other lines are like a conic that hits 5 of these, or a line that goes through 2 of these. Take the proper transform of that. So yeah, you can construct the rest. So yeah, cubic surface, we'll revisit this example a couple more times. Just it's a useful example to work with. Oh, and the proper transform of the boundary here. So if you actually embed this in P3 as a cubic hypersurface, you can find a hyperplane section whose intersection with this is the toric boundary. It is these 3 lines, the proper transform of those 3 lines. So your boundary D. So then the complement of D will be an affine cubic hypersurface. So just something cut out by a degree 3 polynomial in X and Y in affine space, in affine 3 space. So I'm going to review some basic stuff about toric surfaces. I've been talking about them. We'll continue to, so I'm going to say a little more about them. So kind of a refresher or review of toric surfaces. When you study them, you start with a choice of lattice n, which these are surfaces, so it will be z squared. So rank 2 integer lattice. This will be the co-character lattice. We let m be the dual lattice. Let t sub n denote the algebraic torus associated to n by doing n tensor c star. So if you actually take an isomorphism of n with z squared, this tensor product gets identified with c star squared. You can also identify that with Hom from m to c star. And you can think of that as scheme or variety if you want. You can view that as spec of C adjoint M. So the scheme associated to the ring, C adjoint M. So this ring, whenever you have a lattice M, or more generally a monoid M, we'll just deal with lattices for this talk. Actually, no, that's not true. I have a monoid down here. So whenever you have a monoid M, you can define C adjoint M as, well, like this. It's a C adjoined. You have a element z to the m for every element m in your lattice. And then you have relations z to the m1 times z to the m2 equals z to the m1 plus m2. This is addition in your monoid or in your lattice. So basically, another way to write this, since m is rank 2, we can think of this as C adjoined x to the plus or minus 1, y to the plus or minus 1. You can identify these two. And now, any array of rational slope, or any array in n tensor q. So you think of this as q squared. Tensoring this with q to get q squared. The rays will correspond to boundary divisors for partial compactifications of your algebraic torus. So, for example, if you choose a ray, let's see. So, if you add in one ray, you might get something like the x-axis or the y-axis, or you might get the axis at infinity or various things in between that would come from blowups. So, how exactly does this work? So, let's choose a generator n for the ray rho. That A sub rho denote the ring generated by it's the subring of C adjoined M, generated by the monomials Z to the M, where M has non-negative dual pairing with this generator N. So say that say this is our N, and let's say we're looking at this ray. So we can let this be our vector n. So dual to this, so here I'm drawing an n, so an m. So dual to that ray, we have this half space. And then corresponding ring for that half space would be something like C adjoined x comma y to the plus or minus 1. So we're not allowing x inverse anymore, just positive powers of x. Now you could take spec of this ring, the variety corresponding to this ring, and so since we're not dividing by x anymore, we now allow x to be 0. So we've thrown in the y-axis where x equals 0. So that y-axis would be our new boundary divisor in this case. So in general, d rho, or I might denote that dn, that's spec of this ring minus the big torus orbit, that algebraic torus we had before. So it's, in other words, it's the new boundary divisor. With this example, it's the y-axis. You're throwing in the points where you're no longer dividing by 0. Okay, so now we have this correspondence between rays in n, or rays in n tensor q, and boundary divisors. And remember, to specify a Looijenga interior, all we need to do is say, what points we're blowing up on the boundary. We just pick some boundary divisors and say we're blowing up some non-nodal points in those, and that will basically determine our Looijenga interior. Of course, you could, it's not quite enough to just know which boundary divisors you're doing your blowups in, because you could choose your blowup at one point and then you could slide that around in that boundary divisor. That will just correspond to deformations of your Looijenga interior. For the most part, that won't have too big of an impact on your geometry. So I mentioned before, we're only going to care about these up to deformation for the most part.
I know this is very basic, but again, I think it's easy to say and might be helpful. Can you say what a deformation means in this context, so that people don't miss it because of not knowing the word?
Yeah, all I really mean is you're choosing your blow-up points on the boundary, and these non-nodal points that you blow up on the toric boundary, and you could choose your point here, or you could slide it along, blow up some other point here. and that's deforming your surface. Yeah.
So can I maybe the underlying smooth manifold is the same, but the complex structure that you get on this changes by the choice of which point you're blowing up. Okay, so that's what it means. It deforms the complex structure of this smooth manifold. Okay.
I think it's right. So choosing different blow up points, right? That you can view that as just deforming the complex structure. I think so. So right up to those deformations, all we need to do is say which boundary divisors we're doing our non-toric blowups on. So here this slide, I'll tell you a way to basically just list off those boundary divisors. We'll let E bar be a set of elements VI parameterized by some index set I, finite index set. So this will be a finite set of primitive elements in N. We'll assume they're primitive for this talk. Primitive meaning they're not equal to a positive integer multiple of some other thing in your lattice. Okay, and then we can blow up a point on dvi for each index I, and that will give a toric model for some Looijenga interior U. So a toric model is up to deformations, like I mentioned. It's determined just by specifying these VIs. These determine what boundary divisors you're doing your blowups on. So yes, this U is uniquely determined up to deformation, and every Looijenga interior can be constructed in this way. Now, up to isomorphism, we actually don't quite need this much data. We can get away with even less. So that's that omega be the standard skew symmetric pairing on the lattice N. So if we choose a basis, we can let E1 dual wedge E2 dual be this element in the exterior algebra of the dual. Gives you a skew symmetric pairing on N, and all that pairing is it's omega of U comma V is the magnitude of the cross product of U and V. Just to think of it in a basic way, you might even see me doing right-hand rule to check my signs on stuff. So yeah, just magnitude of the cross product. Take that skew symmetric pairing on N. And so if you take an isomorphism or an automorphism of N, that won't affect the isomorphism class of U. So up to isomorphisms, all we, you don't actually need to know exactly where these vectors are. It suffices to just give this matrix, the skew symmetric matrix omega of VI, Vj for all I and j in your index set. So that will give you a rank 2 skew symmetric matrix. Rank 2 is in the row rank or column rank is equal to 2.
Sorry, can I ask? So do you really want to take primitive elements, or shouldn't you be allowing blowing up many points on the same divisor somehow?
Yeah. So you can. So these VIs. So I said set. I should maybe say multi-set.
Yes.
Yeah. So.
But then I think if you want to record that data in the skew symmetric matrix, wouldn't it be better to say not primitive elements and let that kind of
yes, that is another way you could do it. So right, instead of multi-set, by that I just mean you can take the same VI multiple times, and that allows you to blow up the same points on the same boundary divisor multiple times. But right, you could instead just choose a non-primitive point. So choose something that is, instead of choosing k copies of some VI, you could choose something of index k in that VI direction. And you could do that too. So I'll talk about blowups and mutations in a bit. I can come back then and explain the kind of subtle difference, but it's true that gives you essentially the same Looijenga interior as if you keep the VIs separate. Technically, I would say that the way you should view it is if you have something of index k, then you're doing like an order k non-toric blowup, so blowing up a reduced point. And that's almost the same as just blowing up the same like blowing up k points, or it's like blowing up the same point k times. But you kind of end up contracting some curves at like your -2 curves at the end and get a singular point. So I'd say if you want to allow for Looijenga interiors with some orbifold singularities, then you would want to allow non-primitive elements. So yeah, I think I'll come back to that in a few slides. Remind me when I talk about mutations if I forget.
Okay, so I think maybe it's what the simple answer is that we just allow it to be multi-set. I think that's
Yeah. Yeah, right. If you allow it to be a multi-set, then yeah, you get multiple blow points in the same divisor. So now the data, a lattice n with this finite set of vectors e, I called this e bar in the previous slide, and integer valued skew symmetric form omega. This is some version of what people might call a seed in cluster algebra theory. Typically, one would also require that these basis elements E, or that these elements E form part of a basis. And I just allowed any set of elements, and in fact, any multi-set of primitive elements. You could, right, so this doesn't quite fit into, I guess, the way one would normally define a seed. So the thing that people would normally call a seed, you would get like this. You take the lattice freely generated by these VIs, call them VI tilde in this lattice, call this lattice n tilde. And then there's a natural map from n tilde to n, given by VI tilde maps to VI. And you can use this to pull omega back. You take omega on n and pull it back to n tilde. Or another, you call that form omega tilde. And another way to say that is omega tilde is the form on n tilde defined by this. Omega tilde of vi tilde vj tilde is just omega vi vj. It's the same as pulling omega back from here to here. So now, if you, so given a seed like this, with n tilde, omega tilde, the vi tildes, given that version of a seed, you can construct a pair of cluster varieties, often denoted A and X, following Fock-Goncharov. And I'm not going to go into a lot of detail about these. You'll see them in other talks, but I want to mention the connection here so that if they come up again in later talks, you know the connection to this. So this cluster variety is usually denoted X. This has a fibration over an algebraic torus, where the fibers will be whatever the rank of omega is, or the rank of omega tilde. So for us, the fibers will be two-dimensional. So sorry, the dimension of the fibers will be the rank of omega. So two-dimensional for us. And in fact, the fibers will be Looijenga pairs. If your omega is two-dimensional, or if your omega is rank 2, or omega tilde is rank 2, then yeah, the fibers of these X spaces over this torus will give you Looijenga interiors. And you can actually view this X space as a sort of universal family of Looijenga interiors that are deformation equivalent to U. So that the different fibers will just correspond to just moving your blow-up points around or deforming the complex structure. Okay, so we'll be working with some, well, usually with some fixed fiber of the X space, but occasionally I'll mention that you might have to deform or allow for deformations. So yeah, so when people are talking about cluster varieties, they're just kind of an extension of this, or very closely related to Looijenga interiors, Looijenga pairs. So for our purposes, I'll allow the C to be this, that is n, these VIs and omega. I won't pull back to n tilde. It won't really matter for us. So we'll call this data a seed, and the data of a seed determines a quiver Q. Basically, the vertices of Q will correspond to the indices of this set I, and the number of arrows from a vertex I to a vertex J will just be given by omega of VI Vj. And if that is if that skew pairing is negative, then the arrows will actually go the other way from J to I. And since omega is skew symmetric, this is well defined and it gives you a quiver without any oriented 2 cycles. You can have arrows go from one vertex to another, but they won't go both ways. No 2 cycles. Okay, so now this seed, the seed S is called acyclic if the corresponding quiver has no oriented cycles. So I've said there will never be oriented 2 cycles, but what about a 3 cycle like this? That could happen, but if this never happens, you say your seed is acyclic. Okay, and then the Looijenga interior U is called acyclic if it can be represented by an acyclic seed. And then some more terminology, we'll say that U and the seed S are of finite type if the quiver Q is Dinkin. So if it's a type ADE Dinkin diagram, it'll always be simply laced for us because omega skew symmetric. You could also allow, there's a generalization where you allow skew symmetrizable omega, and then you could have other Dinkin diagrams, not just the simply laced ones. But yeah, so when it's finite type, Q will be Dinkin, and it turns out, I think due to Fomin-Jolovinsky, I think they're the ones who showed this, U is finite type, the quiver Q is Dinkin, if and only if U admits only finitely many toric models. Or if the cluster algebra has only finitely many clusters, would be the way to say that in cluster theory. But clusters in the theory of cluster algebras correspond to toric models in our setting.
I don't know. Is that true? I feel like what if you have 2 vectors that don't make an area of 1? Like, wouldn't that have infinitely many toric models? But this thing doesn't. It's not.
If I have 2 vectors that
And it's not thinking, so there's no contribution.
Oh, I see. Yes, I see. Oh, it's not. I see.
Okay. So I don't know if you have 2 vectors, I can quite hear it.
But you couldn't hear that? Is that?
Sorry?
You couldn't hear that? That was too far away?
I just missed a couple words. If you have 2 vectors that what was the question about? Or what was the example you asked about exactly?
I was just asking about if you have 2 vectors whose area isn't 1, but then the diagram wouldn't be one.
Right, yeah. So you would make it something like maybe 2 arrows or maybe more arrows. But yeah, that wouldn't be Dinkin then. So yeah, in those cases, you would have infinitely many clusters, infinitely many toric models. So right. So that's what happens there. So we'll see. So in the next few slides, I think, or it's coming up soon. See how given one toric model, how you can mutate to get another toric model and then mutate again and again. Yeah, so this slide. Right, given one toric model, you can apply mutation with respect to any of your indices I. So here's how mutation works. So this is mutation with respect to the index I. So what we can do is, let's see, we start with our toric model. So we start with the toric variety that we do whatever non-toric blow-ups of to get to our Looijenga interior. And I'm gonna take that C star squared and throw in 2 boundary divisors to make it P1 times C star. So I have the boundary divisor corresponding to VI, and I'll think of that as 0 times C star. And the boundary divisor corresponding to negative VI, we can view as infinity times C star. So in other words, I'm considering the toric variety whose span includes 2 rays, VI and negative VI. And this is view this as a fan in two-dimensional space. So it gives you a toric surface. It'll give you this one, P1 times C star. Now, so that's the picture. So that's what's going on over here. I have P1 times C star, and here's dVi. And inside there, I'm going to choose a point, call that point H plus. That's this point. And I'm going to let F denote the P1 fiber over this. So this fiber is F, and we have a map that just projects down to dVi, just collapsing all these P1 fibers. So F is the fiber over that. Now we blow up this point. That gives us an exceptional divisor. Call that E tilde for now. Exceptional divisor E tilde. And then we can take the proper transform of F under that blow up. Call that proper transform F tilde. And now, so F before had self-intersection number 0. It was a fiber. When you blow up a point on a curve in a surface, and everything's smooth, that decreases the curve self-intersection number by 1. So the self-intersection number was 0. Now it's -1. And a -1 curve in a toric surface can be blown down, or a -1 curve in a surface can be blown down to a smooth point. So now we blow down F. So we blow F down to this point. I'm calling H minus here. So we have a birational map from this picture over to this one, given by you blow up this point and then blow down this curve to this point. And Gross, Hacking, and Keel in their birational geometry of cluster algebras paper, they show that this blow down procedure always gives you a toric variety. It always gives you a new toric variety. So we started with the toric variety, we got a different one. And maybe just assume for right now that our seed has only one I, only one VI. So our Looijenga, we can say that our Looijenga interior, just for the sake of example, suppose our Looijenga interior comes from just blowing up this one point, this one non-toric blow up. So in other words, the Looijenga interior is what we have up here, minus the boundary divisors. You can think of that as you take the algebraic torus here and the algebraic torus here, and you glue them together. You glue them together using this birational map, because the birational map, a birational map is the same as an isomorphism between Zariski open subsets, Zariski dense subsets. So basically, the Zariski dense subsets here are everything except for F, and everything except for F in the boundary, and then everything except for E in the boundary. And when you glue those together, well, from this picture, you're able to see F. You get everything except for E. And then this picture adds an E. So when you glue those two together, you're actually getting the full Looijenga interior, the full blown up thing, except for one point. You actually miss the point where F and E intersect, because this point would correspond to this one in the left picture, and sorry, I have that wrong. Correspond to this point here, this point, and this one. So it lives in the boundary in each of these pictures. So it gets missed when you glue the tori together. But that's a point in a surface. It lives in codimension 2. And if you're interested in things like global functions, like if you're doing mirror symmetry and you care about theta functions, codimension 2 stuff won't matter. That's Hartog's theorem, or an algebraic geometry, comes from Sear's condition S2. Basically, if you change something in codimension 2, like throwing away a point like this, that does not affect your regular functions, or it does not affect your sections of line bundles. So we missed that point, but it doesn't matter. So when setting cluster varieties, you view it as gluing together a bunch of algebraic tori via these birational maps called mutations. But you can instead view it as you just do some just do a blow up for each of, for each VI, you do some non-torque blow up. And the mutation is just the blow up followed by a blow down to a new torque model. And now if we had a whole bunch of VIs, you could do these mutations for any of the VIs, and glue together using all those different VIs, glue together all those algebraic tori, and together all of those give you your full Looijenga interior up to codimension 2. Oh, and is there a question?
So how is it easy to see how the toric model changes? Like you have to do some toric blowups so that you have the other boundary component in your model or something like that?
Let's see. Yeah, so if we had some, maybe if we had some other VIs.
But let's say we didn't have the top thing.
Yeah, so we include that top boundary divisor just so we can make sense of this picture, but right, you might not be doing any non-torque blowups on that, but you can include as many torque boundary divisors as you want, and that doesn't affect the interior. So we just kind of throw them in for convenience.
But that kind of changes that toric blowups, like that adds nodes to the seed, right? To the seed graph, like.
Right. Yeah. So each VI, each non-torque blowup you're doing, right, corresponds to a node on your quiver or some index. So if we maybe had 3 non-torque blowups we're doing, you can mutate with respect to this one and do this blow up, blow down, or you can maybe mutate with respect to another, do a different blow up, blow down, and so if I blow up this one and then do this blow down, these you still want them to live on the same boundary divisors, but those boundary divisors will correspond to different points in N in a way that I'll talk about in the next couple of slides. It does change your lattice structure a bit.
Okay, so maybe I should wait.
Okay. And I have written here, you can write down an actual formula for what this birational morphism or birational map is. And I mean, this is it. It's z to the m, where m is something in your dual lattice. So basically, binomial z to the m just gets multiplied by this binomial to some power. So ai is some constant. So you take your binomial ai plus z to the omega of vi comma blank. You can view that as living in your dual lattice. And then you raise that to the power of the dual pairing between vi and m. Consume. So the place where this is 0 will be, or you look at where this is 0 intersected with the boundary divisor dvi, and that's this point h plus. So changing the constant ai just moves h plus back and forth. Right, and then you raise this power. If vi was non-primitive, then this exponent, see, like if you replace vi with 3vi, that would triple this exponent. So that would basically correspond to you mutate and mutate again and mutate again. Like you're mutating 3 times at once, or index of vi many times at once. So you do this, blow up, blow down, blow up, blow down, blow up, blow down, and so you get, when you do all 3 of those at once, you only see the final exceptional divisor. The first 2 are being contracted. They're missing, and they'll, if you try and put them back in, you would either have some extra -2 curves, or depending on how you do it, they might be, you can fill in these missing points as being singular points. They would be some type like an singularities, or type a sub index of vi -1 singular points. So leaving that out for this talk mainly, but I wanted to mention it. Let's see. Right, so you could allow for non-primitive vi that way. Okay, so yeah, as mentioned, this blow up, blow down does kind of mess with your seed data a bit. It'll mess with right, how you describe your torque model. So I'll describe one reason why that happens. So this is some more refresher of basic torque geometry. There are some important facts from torque geometry. So let's that Y be a complete non-singular toric surface, boundary divisor D, components dn1 through dns. Say these ni's are primitive generators for the rays for these boundary divisors. And that C be any curve class in Y. Then it turns out that if you sum over all the different indices I going from 1 to S, of C intersected with dni, take the intersection number, times ni, times the vector ni, that sum will equal 0. So the basic example is the fan for P2 is generated by 3 vectors, or you have 3 rays generated by the vectors 1, 0, 0, 1, negative 1, negative 1. This is kind of the standard fan for P2. And if you take any curve, if you take a degree D curve in P2, that'll hit each boundary divisor D times. So the sum would become D times this vector plus D times this vector plus D times this one, and that equals 0.
I think it should be VI from not
Sorry?
should be
Oh.
VI.
Oh, so these ni's. Yeah. So previously I wrote VI for. So I write VI for the boundary divisors where I'm doing non-toric blowups. Here I'm just denoting the just whatever the boundary divisors for my toric variety are. So I'm using ni, but I could use VI, but there's no repetition of the ni's here. These are these are enumerating all the boundary divisors for your toric variety. All right, so let's look at the special case where the curve C is actually one of your boundary divisors. So this equation works for toric varieties in any dimension, but in 2 dimensions, your boundary divisors are also curves. Your divisors are curves. So we could look at where C is just dni, and so let's assume, so I didn't write this, but let's assume that these ni's are cyclically ordered. So maybe this is dni, dni minus 1, dni plus 1. And I'll say S plus 1 is 1, so they're cyclically ordered. Now the intersection number of dni with the boundary divisors, well, it has 0 intersection with most of them, with all these, but the intersection number will be 1 with the adjacent boundary divisors. So that gives us, so in the summation now, the coefficients for I minus 1 and I plus 1 will be 1. And then the only other term that doesn't vanish is the I term, the one where the coefficient is dni intersected with itself. So we have this equation should always be satisfied. Ni minus 1 plus the self-intersection number of dni times ni plus ni plus 1 should equal 0. So that's the equation we just had. Now, when we mutated, if we do a mutation mu j with respect to the index j, or the direction vj, so remember we blow up a point on dvj when we do that, and then we blow something down to d minus vj. When you blow up a point on dvj, that decreases the self-intersection number by 1, and then the blow down will increase this self-intersection number by 1, the self-intersection number of d minus vj. So if you're changing these intersection numbers, that this equation won't be satisfied anymore. So one way to think of that is the lattice structure of n is changing. addition in n before the mutation is different from mutation after, or is different from addition after the mutation. Another way you can think of that is you could say n is the same for each of these, but your vectors vi are changing. So in other words, you can apply a piecewise linear map between your lattice n for your first toric variety and your lattice n for the new toric variety that you get after mutation. These are two different co-character lattices, but there's a piecewise linear map you use to identify them. And then if you identify them, the way that this piecewise linear map acts on these vectors vi is like this. So vi, or the vectors vi will map to these vectors vi prime, where vi prime, well, if I is equal to j, then you just get, vj prime is negative vj. And that's just because, we did a toric blow up on the divisor corresponding to this direction, and then we blew it down to a divisor corresponding to this direction. So vj changes to negative vj just because we blew down to a different divisor. So that's what's going on with this one. And then with the other VIs, they change basically because these intersection numbers are changing.
Sorry,
So-
I still kind of feel like this VI should not be primitive. Like I feel like that's how, for example, like if you have a toric divisor and you don't blow it up, right? Then you should actually not have a vortex for them.
Right, so so these VIs are not assumed to be the rays of my fan. Since I don't necessarily, if there's some boundary divisor for my Looijenga pair that won't, where I'm not doing any blowups, then I just won't have a VI for that direction.
Okay, so S is in for N's and S for B's is different. That's just a typo.
Right. Oh no, it's the. I see what you're saying. So you can choose your fan to include, all of the rays generated by the V's and also maybe some additional rays. And then the generators for rays of your fan will be the N's. And the N's are chosen to be cyclically ordered, and they're all distinct and give you all the generators for some non-singular fan. And then these VIs can be some subset, or generate some subset of those rays, maybe with multiplicity. Like you might have repeated directions, but you don't have to include every ray. I don't actually want to specify what the boundary is because we only care about the Looijenga interior. So I'm not actually specifying the fan. I'm just saying you could, for the sake of understanding what happens to your toric model when you mutate, you could throw in some rays to your fan that make it a non-singular fan with directions, including all these VIs and the negative VIs and maybe some additional directions.
Okay, I think I understand. My only comment then is that again, these S's are different. Like there's not a one-to-one correspondence between B's and N's, right?
Oh, did I use? I see. Yeah, so I used S hair and S hair, and I should have used different letters for those.
They're unrelated, and this N's only come up if you. Okay, I think I understand.
Like
Okay.
the N's are the rays of a fan for the toric model.
But that's not something that
and
speaks
the
for
V's
them.
are a multi-set of N's, which are the non-toric low.
But that's only if I want to interpret something, I need to look at these N's. Otherwise, my seed doesn't have this N's in it.
Hmm.
Yeah? The N's just come up when I want to interpret something geometrically.
Right. Yeah, the N's are like some placeholders that you throw into, to give you something to blow up on or blow down to. Right. So right. So these other VIs or VI primes for I not equal to J, they change by this piecewise linear map where you take your VI and you add some multiple of VJ, and that multiple is given by that skew pairing omega of VI and VJ. If that skew pairing is positive, and if it's negative, then you don't add this at all. So this notation here, this A bracket plus, means you take the maximum of A and 0. So you add this if it's positive, otherwise ignore it. So quick little example. Oh, what just happened? Here we go. So say I have these three directions. Maybe these are my V1, V2, V3. And let's say I mutate with respect to V2. After I mutate, V2 will be pointing this way. V3 will still be going the same direction because omega of omega of V3 with V2, you do your right-hand rule, figure out that that's negative. So this is V3 prime, V2 prime, but omega of V1 with V2 is equal to 1. And so V1 gets pulled down, gets pulled 1 into the V2 direction. So you can see from this, the Looijenga interior where you take P1 times A1 and do 1 blow up on each boundary divisor corresponds to this picture. That's the same as if you take P2 and do 1 blow up on each boundary divisor. That's what these two pictures would correspond to. And so those two Looijenga interiors would be related by a mutation. So they're actually the same thing. So I think I should probably stop because I'm low on time. I think of course, I hope to get. I think I'm at least close to where I wanted to get for this talk. So I'll stop here and then I can continue in 30 minutes, is it?
Yes, exactly.
Okay,
Okay.
let's start first.
Maybe 3 minutes for questions.
Person from the room. I can ask, but maybe to come up or not. But that was you mentioned this acyclicity for Looijenga interior or the quivers, let's say, acyclic quivers. So is there any role? I mean, what's the properties of them? What's special about them?
So in my next talk, I'll have a statement of the following equivalent, and there will be acyclic quivers are equivalent to having a whole bunch of other things. Some examples. Let's see. So I'll talk about these eutrop, these eutrops. So one thing I'll use to characterize. Well, actually, that's not a really good example. All right, sorry. One nice thing they satisfy. You can choose. You can choose all of your blowups, all these VIs that you do your blowups along to live in a half space. You can pick one half space, and they all live in there. That at least if the corresponding quiver is acyclic, you can do that, and that's equivalent actually is that you can choose all your blowups in a half space, and you can kind of see that if they all live in a half space, your arrows they'll only go like counterclockwise. So there's no way that you can get a cycle then. And when that happens, let's see some properties. So there will exist some theta functions, or there will exist some functions, some regular functions, which might be 0 along some boundary divisors. You can take a valuation of some regular function along some boundary divisor and get something positive. It'll be generically 0 at the boundary. And that's true if and only if it's acyclic. Otherwise, evaluations of regular functions on the boundary are always negative. And we'll see a number of other conditions like lines in your tropical manifold. There will exist lines which don't wrap all the way around, whereas in non-acyclic cases, any line in the tropical manifold that I'll define soon will wrap all the way around and maybe self-intersect. And we'll see other properties too.
Okay, yeah,
So
thanks.
can I also ask the question? So the graph that you construct from the seed, it determines everything, right?
The graph, that quiver, that graph, that determines everything. And you could, of course, mutate, and that mutates your quiver. There's a version of quiver mutation. The quiver up to mutation totally determines your Looijenga interior up to isomorphism and deformation.
Okay, Okay, thank you.
Yeah, other question from the room?
Maybe I should mention much more generally, cluster algebras. A lot of people will look at special cases of cluster algebras where the quiver is acyclic, and there's a number of nice properties in general that are known for acyclic cases, but not known in other cases because they either don't hold or they're just harder to understand.
So maybe, is there a question from online participants? Okay, not, then let's thank Travis again and we will meet in 40 minutes. Yeah.